If you didn't try this example, please go ahead and push pause and try this example on your own. If you have got an answer, this video will show you how to accomplish that. So we want to use Newton's method to approximate a solution for an equation. That equation is x times cosine x equals 2x minus 12. Our initial guess is going to be x sub 0 equals 1. And we're going to approximate to 2 decimal places. We have x times cosine x equals 2x minus 12. We want to start with an initial guess of 1. By the way, we've used 1 a number of times. It doesn't matter what your initial guess is. You can start an initial guess at anything. But remember, if you start at a different number, you might get a different root than what I get if I start at 1. So be careful about that. I'm going to create a function. I'll call it once again h of x, just like I did in the last problem. And what I'll do is I'll make sure that h of x has the roots, which will be equal to solutions of the equation. So I'll subtract 2x and add 12 to both sides of the equation, and that will give me a 0. And if I let h of x equals x cosine x minus 2x plus 12 be my function, I know the roots will match up with solutions to the equation. Since I'm dealing with the function, let's take a derivative of that function. This first part, we have to remember how to do a product rule. So derivative of the first piece is 1 times the normal second piece plus the normal first piece times the derivative of the second piece. Derivative of the second piece is negative sign. So I'm going to change this plus to a minus. Derivative of negative 2x is simply negative 2. Derivative of 12 is 0. So my derivative is cosine x minus x sine x minus 2. Let's start with an initial value, initial guess of 1. If I plug in 1 into my function, 1 times cosine of 1 minus 2 times 1 plus 12 gives me a 10.54. That's way off of the line. So way off the x-axis. That's pretty far away from being a root, right? 10 units up. If I do my derivative at 1, cosine of 1 minus 1 times sine of 1 minus 2 becomes negative 2.30116686. Let me round that to 6 decimal places because that's what we've been doing. So 6 decimal places would be there. We take our first iteration of Newton's method, 1 minus the fraction 10.540302 divided by negative 2.301169. I ended up with 5.580412 when I round to 6 decimal places. Once I plug in the initial iteration, my second guess there, into the function h of x. So once I plug in the 5.580412 into my function h, I ended up with 5.097324. If I plugged in that number, 5.580412 into the derivative, I ended up with 2.3698,758. All right, let's see where that puts us. That puts us, let me just copy and paste, in a weird spot, and we'll start seeing why. So take 5.580412, subtract this fraction, which has a numerator of around 5.09 and a denominator which is close to 2.37. When you type in that number into your calculator, you end up with approximately 3.4295. 30, rounded to 6 decimal places there. And you think, well, that's another number, so let's do it again. Let's give another iteration. All right, in this case, I go h of x2, I'm not gonna write the number out there, h of 3.42 approximately, gives us a 1.852598. Now, that's closer to 0 than 5.09, but didn't get me super close to 0. H of x2. Well, what did that get me? H prime of x2 got me negative 1.984931. Okay. Let's do one more iteration, and then I'll show you what's going on here. What's different about this one versus the other. So take our second value, minus fraction, and the numerator of that fraction, it's the output of the function. In the denominator of the fraction, it is the output of the derivative. So first off, what is that number? Let's calculate it. So that number is approximately 4.362857. If I try to find the function value at that number, that 4.362857 number, I get an output of 1.7801,902. And you might get really excited and say, oh, that is slightly closer to 0. But notice that's only slightly closer to 0. That's not, we're not getting super duper close to 0 like we did in the previous examples. What about the derivative at 4.362857? 0.362857. Well, the derivative I got was about 1.7565904. You might say, man, this is taking a minute and we're not getting super duper close to zero. If when you did this on your own, you did a couple other iterations and you kept getting numbers which were around 1 or a little bit more than 1, you can never get below 1. There's a reason for that. Notice that these derivatives are changing from negative to positive. In other words, in one iteration, we went to the, we went from 10 down to 5. We went down to 1.85, down, excuse me. Let me restate this. So we started at 1, and then we went up to 5.58. And then from 5.58, we went down to 3.42. And then we went back up to 4.36. What's happening is Newton's method basically got stuck. So here's what's going on graphically. Graphically, we started at a place at positive 1. And I just want you to notice that at positive 1, that is before our root, but there's sort of a dip in between our root and the negative 1 where we started, or the positive 1 where we started at. This would have happened if we'd have started at 2 as well. So what happens is that this method, when we get up to 1, it takes my approximation, and my next approximation is about 5.5. Well, 5.5, if I draw a tangent line 5.5, it's going to force us to go back the other way. So it's going to force me to go back the other way. And then if I draw a tangent line here, it's going to force me to go to the right a little bit. And now we're going to be forced to go to the left a little bit. In other words, Newton's method is trying to approximate the root by utilizing tangent lines, but that means that these little dips, which cause relative minimums, Newton's method can get stuck in. So Newton's method essentially started at 1. It got me over to here, but then because the tangent line here is forcing me to go in a negative direction, it's a positive slope, but forcing me to go into the negative direction, it forces me backwards. And we kind of got stuck in this little dip here. And so we never got a number which was actually close to 0. That can happen with Newton's method. You can get stuck in these little dips and never be able to get out of it. Now, the way to avoid this is to, if you do get stuck in a little dip like this, look at the graph of the function and start between the relative maximum or relative minimum and the actual root. If you start somewhere in this region, Newton's method will work really nicely. So that's just a note on Newton's method. If you wanted to always avoid these dips, then you should just start between a relative maximum, relative minimum, and our root. And you can always look at that, or I should say, you can always, approximate that by looking at a graph of the function. So for instance, if we would have started at about 7, we'd have been just fine. Or if we'd have started at 8, we'd have been just fine. So Newton's method can give us that issue where we get caught in a dip, and instead of giving us a root, it's essentially just approximating a relative minimum in this case. And the same is true on the other side. If I would have started over here, I might have gotten caught in this relative maximum. So it had told me to go up, then I get over here and it told me to go down. And I got stuck at this relative maximum. So Newton's method can eventually, also, if you're smart about Newton's method, can find the relative maximums and the relative minimums as well. All right, we're not going to do that in our chapter, but that's what we'll do. That's what I'll say.